So most of these here at the beginning are pretty straightforward. We saw a lot of these on the quiz, in the quiz review. Number 2, the one thing I would tell you here is f of x is really y. And so because we're doing the inverse, we're going to flip-flop the x and the y. And what you got to be careful of is wherever the -7 is at. The -7 here is underneath the radical. And so if it was outside the radical, I would add 7 first. But because it's underneath the radical, we got to get rid of the radical first. And so we got the opposite of taking the cube root of something would be to cube both sides. And then we could add 7. And then they're just writing it in inverse form, f inverse of x. All we're really looking is which function does it give us. Okay. So just be careful. If the -7 would have been on the outside of the radical, we would have added 7 first. And then we would have cubed both sides. And so then the answer would have been D. Number 3, you just got to graph it and then tell if it passes the horizontal line test. It's just a yes or no. Okay, 4 is a calculator problem. 5 is a calculator problem. You can put it in the graph. Give me a few points that would be on that graph, and then just graph it. Same thing on number 6, but make sure that you describe the changes that take place. Some people have kind of asked me, like, what are we comparing it to? Y equals 2 to the x is what we would call the original function. You don't necessarily have to graph the original function. If you want to, you can, just to show like the changes that are taking place. But that's the graph we're comparing it to. So the 2 is part of the original equation. There's no changes that the 2 is doing. And so on the quiz, some people were trying to tell me what the 2 was doing to the graph. The 2 is not doing anything to the graph. At least this 2 is not. This 2 is up in the exponent, so that 2 up there is changing it. Whatever's connected to the x is going to be left or right, and it's going to be opposite. Whatever is at the end is going to be up or down, and it's going to be the same as the sign that you have. So in this case, we would say right 2 and then down 3. And then we want to graph it. One of the first things I would probably encourage you to do here is originally our asymptote is the x-axis, but it's going to be moved down 3. Because the graph is going down 3, then the asymptote is also going down 3. So I would go ahead and draw that line in there to show where the graph is going to approach. Your graph cannot cross that line, basically. That's why we want to put that in there. Formula sheets, I'll give you the same formula sheet that we had on the quiz. The only thing really different about it is on the quiz, I told you didn't need that box. And when we get to the end of the review here, there will be a few problems where you have to use the formula that's in that box. So 7 and 8 should be pretty straightforward. You're just plugging it into the formula. On number 9, that's the one we kind of talked about the other day. You're going to put these two functions into your y equals, and you're going to graph them both, okay? And all we're looking for here is where do those two functions cross one another? And it is two exponential functions, although when you look at the graphs, it's not growing very fast, so it almost kind of looks like a line that's pretty flat. It's not growing really fast like a lot of exponential functions are, because our growth rate is pretty small here. This is less than 1%, this is about 1.6%. So 13.6 is like the original population in millions. 16.6 is the original population of the other country in millions, and we want to know when will these two countries be the same. So when do they intersect? X is the number of years that has passed by, and we started in 1998. So if I said like 10 years down the road, then that would be in 2008. And then the Y value is the population. And what this question is asking is, what would the population be when the two countries are the same? So we're looking for the Y value of the intersection. And you're going to have to round it, because it doesn't come up to be exactly one of these. So we have to round whatever our answer could be. Also, I told you on Friday that you want to probably change your window, because your population is already above 10 million, then if you just keep it at 10 million for your max, then you won't be able to see the graphs. And so you want to be able to see the graphs. So what I told you on Friday was change your X max and your Y max to 20. If you don't know how to do that in your calculator, I can show you. You just go into your window and change your Y max and your X max. And then you should be able to see the graph. Okay. And then just do your intersect feature that we've done before. If you need help with that one or putting it into the calculator, let me know. Okay, I can't put this one into the calculator like this. So there's two ways that you could kind of go about this one. You could make a table of values, which would be a little bit backwards of what we typically do. Usually we plug a number in because we have an equation in y equals form. Usually we plug a number in for x and we find y. In this case, I could plug a number in for y and find x, because we're trying to figure out what x is, because we have an inverse equation here. So if I said 5 raised to the 0 power, that would be 1. 5 raised to the first power would be 5. So there would be 2 points that would be on this graph. Now, one thing I want to point out, and the other way you could do this is you could change it, especially if you have the log base button in your calculator. You could change it to this. These two are the same equation. This one's the log form, this one's the exponential form. So if you would rather change it to the log form, you're going to get the same graph either way. Now, when I graph this, what happened on this one, first of all, the graph is counting by 2s, so it's crossing the x-axis at 1, 0. When I put this into my calculator, this graph is coming right down here alongside the y-axis. When you put it in your calculator, it was maybe kind of hard to see this point. Sometimes when you look at it, it looks like it stops right here at the x-axis, but if you zoom in just a little bit, I think I showed a few of you that on Friday, that if you zoom in a little bit, it comes right down here alongside it. So on the quiz, a lot of people stopped it right here because that's what it kind of looked like on the calculator. If you zoom in a little bit, that's where you're going to use the log loop rule. That's on your formula sheet as well, where you're going to change it from log to exponential or exponential to log. Go back and forth between the two on those. Change a base formula. You can either put it in just like that if you have the base button in your calculator. If you don't have the base button in your calculator, you're going to take the log of 189 divided by the log of 6.5. Make sure you close the parenthesis off after the 189 so it puts it in correctly. This is kind of like the one we did with exponential earlier, except this is with the log function. You're going to talk about what type of change is taking place, left, right, up, or down, and then graph, the new graph. Okay, the original function in this case is y equals log x base 5. Okay, the 5 here doesn't do anything to the graph. So when you're saying what type of changes take place, it's either got to be the number attached to the x or it would be something at the end. In this case, because the plus 4 is in the parenthesis, it's attached to the x. If I wrote something like this, then here the plus 7 is not attached to the x, it's at the end of the function. So this one would move it up 7, okay, because there's no parentheses. So there's a big difference between this and this. The parentheses tell me it's attached to the x. No parentheses means it's at the end of the function, which means up or down. So just keep the two changes in mind there. Those are the different ones that we've talked about. Okay, 17 is just plugging it into the calculator and evaluating. Remember your log rules and properties that we talked about? You're going to expand or express as a sum or difference of logs based on how it's written out. And then there will be a couple on the next page where you're going the opposite direction, where you're going to simplify and go to a single log. So if I see a plus sign in between two logs, then that tells me I'm just going to multiply the 71 and the 2 together. So you just got to know what those properties all are. Most of those shouldn't take a ton of time. It's just a matter of rewriting it in a different way. Okay, 22. We had a couple problems like this. Because we have a minus sign in between the two logs, and it doesn't matter if it's log or ln, but we have a minus sign here. We're going to rewrite this as a single log, so we're going to go ln of x squared minus 100 over x plus 10. And a lot of times this is where we would stop. If we can't do anything else, this is where we would stop. But this kind of takes us back to the rational function stuff that we did a while back. If I have rational functions that I can simplify, then I'm going to simplify them. So we got to remember the different types of factoring. The most common types of factoring that we've done could be GCF, could be DOPS, could be product and sum, maybe slide and divide, but probably not going to give you any slide and divide. But x squared minus 100 is DOPS, difference of perfect squares. So we can factor it. Every once in a while, some factoring will pop up. And so what we can do then is I can knock those x plus 10s out. And then we're simply just left with the ln of x minus 10. There's nothing left on bottom. Okay. So if we can factor it and simplify it, then we want to do that instead of leaving it like this. Okay. You got a few more evaluate type problems using your rules. Number 25 with base 3. I showed you a couple of different ways that you could do this problem. You could log it, frog it, solve it, because we have a variable in the exponent. There's nothing wrong with log it, frog it, solve it here, okay? But I think probably the easier way, if we can do this, is rewrite both sides as base 3. Okay, and sometimes I may not be able to do this. But in this case, if 9 is a power of 3, then I can rewrite 9 as 3 to some power. So if I take 3 squared, I get 9. So I'm rewriting 9 as 3 squared. And the reason I think that's a piece of cake now is because as long as these two are the same base, which they are, they're both base 3, then the two exponents have to be equal. So all I got to do is say 10 minus 2x equals 2, and then solve for x. It's just a two-step equation. Okay. I think that's slightly easier. If you don't want to do it that way, then you can log both sides, jump the exponent in front of the log. There's just more steps to it. And you could just plug it into the calculator, but it's a little bit more lengthy, I think. On this one, set it equal to 0. This is the one I kind of compared it to like a quadratic equation. It's not a quadratic equation because we don't have x squared in it, but it looks very similar to a quadratic equation, and we can solve it very similar to a quadratic equation. So the easiest thing to do here would be put it in my calculator, graph it, and then just find out where does it cross the x-axis. So you can do this whole problem in your calculator. Okay, then you got some different logs. Remember that I think the hardest step is always to try to decide what am I going to do, what's my process going to be. Okay, you can use the log loop rule. You can use your log properties where you're combining logs together. So like on this one here, I think using the log loop and changing it to exponential would be the easiest way to go about it. This one here, because I have multiple logs on the right-hand side of the equal sign, I want to combine those logs together first. Okay, so you got to kind of figure out what your process is going to be, and then you just got to apply the rules to it. I'll let you try to do those. Solve for x. Okay, these last three is where you're going to use the formula that's in the box. We didn't use that formula on the quiz because we hadn't gotten to it yet. But that's what the last three problems are dealing with. All you have to do on number 29 is write the equation of the function that's being represented. So there's no solving or anything. Which one of those represents the correct equation? And that's the equation from the box on your formula sheet. The formula that you need to know whenever you see the word doubles, because it's doubling, we're going to do the ln of 2. If it was tripling, we would do the ln of 3, but doubling is the one we saw most often. Okay? If I know the number of years or the time, then I would use this formula. So I'm going to take the ln of 2 and divide it by 19.25, and it's going to give me my k. If I knew the k value, I would plug that in here and solve for t. Okay, now, here's what I'll tell you is it is going to give you the k value as a decimal, and then we want to change it to a percent. Okay, so write your answer here as a percent. So you're going to have to move the decimal over 2 places to do that. Because whenever we talk about what is the growth rate, we always talk about the percent. I'm going to kind of help you set number 31 up, and then I'm going to let you try to solve it on your own, but just kind of showing you what goes where. We're going to use the formula that's in that box. P sub 0 means where are we starting at? Okay, so over here, we're currently at 66 million. And I'm just gonna write 66. I'm not gonna put all those zeros on there. Just know that it means million, not 66 cars. E, raised, and we know that K is 7.6%. So this is what I was talking about a second ago. When we plug it into the formula, we're gonna put it in as 0.076. We can't just put 7.6 in there. So we have to put 0.076. We're trying to find the number of years. So we're trying to find T that it takes to get to 44 million. And here's the other thing you gotta be careful of. It's decreasing, and so we're gonna make the K value negative. If it was increasing, and we know it's decreasing because it says decreasing, but if we start out with 66 million and now we have 44 million, that also tells me that it's decreasing. If this number is bigger than 66, then it would be increasing, and so then that K value would be positive. So that's the one thing you want to pay attention to on that. And then you just want to figure out how many years will it take for 66 million cars to reach 44 million cars. How many years will it take for that to happen? So now you're going to solve it. Okay. Any questions so far? I'll let you guys